The James Webb Space Telescope's job was to help astronomers understand the early universe, just the first few 100 million years after the Big Bang. Astronomers have theories, but it's important to test your hypotheses, and that is done with a gigantic space telescope. And astronomers were expecting to find things that they didn't expect, but the surprises have been pretty big. And you've probably heard the news about these universe-breaking galaxies, these galaxies that are like the size and mass of the Milky Way, but only a few 100 million years after the Big Bang. It's not what anyone was expecting, and it has the potential to overturn many of the established theories about star formation, galaxy formation, dust accumulation, quasars, black holes, a bunch of things, dark matter, all coming together with this discovery of giant galaxies too big, too early. My guest today is Dr. Joel Leja. He is a professor at Penn State University, and he's part of the team that used JWST to scan the early universe and found several examples of these gigantic early galaxies. He's working to confirm them. We've got like a little bit of a sneak preview on how the confirmations have gone. Spoiler alert, still exciting. So it's an interesting conversation, really, to see what is the cutting edge of astronomy right now, how JWST is rewriting our understanding of the early universe. So enjoy the interview. So what's it like using the James Webb Space Telescope?
Oh, I mean, it's fantastic. This telescope is something we have waited for and dreamed about for a very long time. I spent my entire PhD thesis looking forward to this moment.
Yep. But like that moment when you've done all this research, you know what you're looking for, you've requested the data, you've seen that the telescope has taken the data, and you first get your hands on it to take a look at it. Did it match your expectations?
Oh, incredible. Actually, it matched it and went well beyond. I think it's healthy to come in with a little bit of skepticism.
Yeah.
And we certainly did. But when the first data from Webb came down, it's been incredible. It's operating well beyond the specifications. And being the first person to find something in deep space, something no other human had seen before, not knowing what it is. And that's just a fantastic and amazing feeling.
Yeah, no, absolutely fantastic. So let's talk about the research. You set the internet on fire a couple of weeks ago with this, and I'm going to use air quotes, universe-breaking galaxies. I suspect whoever was your press officer, had a lot of enjoyment putting together the press release. But what was the discovery that you made?
Yeah, so these objects, there's some pretty unusual things in the sky, and these are from the very first data from Webb. So we weren't expecting to find anything quite this exciting so early, but these are little red dots in the images, and when we run our analysis on them, they suggest that these are galaxies that existed in the first 500, 700 million years of the universe.
And what kind of galaxies, obviously they're just a single pixel red dot, but what do you think, based on your spectroscopy, what are these galaxies?
So we only have imaging so far, and that's really an important caveat. Because,
okay. So you have images, you don't have the spectroscopy yet. Okay.
Yeah, spectra are the next big step. So we don't know the true distance to these things, and so there's a little bit of fuzziness about what they are for that reason.
So I guess then why do you think they're galaxies?
Yeah, good question. So there are many types of objects that can appear in these images. But there are only a few that should have this apparent morphology in the imaging and this particular energy as a function of wavelength. There are a few candidates that are not galaxies. For example, they could be supermassive black holes feeding in the very early universe, which would also be exciting for different reasons.
Yeah, I guess to see quasars that big, that early is a whole other world of cosmology that gets, shaken up. So it's all pretty interesting. But let's go back to this idea that they're galaxies. So I guess when you sort of see these, again, they're just a tiny, as you say, blurry red dot seen at the very limits of what Webb can do. but what makes you, I guess, what kinds or what size of galaxies do you think you're looking at?
Okay, yeah. Well, so if we fit our standard models for galaxies to these little red dots, we get incredibly large masses for these systems. So they existed in the first 3% of the age of the universe, but we're finding masses in terms of stars that look more like the Milky Way or even a little bit higher. And so that was really a shocking finding. We didn't expect to find anything this big this early.
Well, how big were you expecting to find? What do the traditional cosmology theories expect to see?
Yeah, so the size of galaxies in the early universe are very closely linked to the size of the dark matter halos, which are their home. And based on the understanding of how we think halos evolve, which is well understood, we think we know how dark matter works, even though we don't know what it is.
Yeah. Yeah, we use it as a telescope, but we don't know what it is.
It's quite amazing how much use we get out of it without having any idea what it actually is.
Yeah.
But yeah, based on this, we expect to find galaxies maybe 10, 20 times smaller at the biggest. And there's also this additional X factor of how much of the sky we've searched. So this was a pretty small amount of the sky, and we found some pretty big things. So that was surprising in and of itself.
Right. So you are expecting to see galaxies that are 5 to 10% of the mass of the Milky Way at this age of the universe, these building blocks that are coming together. And instead, you're finding objects which are the same size or even more massive than the Milky Way just a few hundred million years after the Big Bang.
Absolutely. It's incredibly startling. It's like going to check on your 2-year-old toddler and finding a fully grown adult in their place.
Right.
You have questions.
You have questions. Okay. All right. So, like this, if true, what does this do to our ideas, our traditional ideas of cosmology?
Well, there's a number of ways this discovery can go. I suspect we're going to learn more about how galaxies form than we are about our theories for cosmology. So in order to turn this light into an idea for what these galaxies look like, or what their mass is, how many stars there are, we have to use models for stellar evolution, models for cosmic dust and gas, to measure the properties of these objects. I suspect what we're finding is that galaxies are forming far than we thought. In order for that to approach the level of making us think about our assumptions about cosmology, I think we're going to need to gather more evidence and get a lot more data and really do some convincing. Cosmology is a strong, well-established theory, and if we want to take a crack at it using galaxies, we really need to make sure our ducks are in order.
Right. So okay. So like, how quickly, I guess one of the questions that Webb's job is to answer is how quickly these building blocks of galaxies came together. And so if these are giant galaxies, then these galaxies are coming together more quickly than anybody anticipated. And so what do you think, you mentioned all of these ideas about dust coming in, about star formation, etc. So if these galaxies are getting to the size of the Milky Way within, so not our theories of cosmology, but I guess all of those separate ideas, gas clouds coming together, star formation, all of those need to be revised and revisited, right? Like that's sort of the implication.
Yeah, I mean, so if these masses are confirmed, which we're working on quite voraciously right now, but if we're able to confirm these things, it implies that these objects formed incredibly fast in some intense bursts of star formation. The kind of process, like, we don't see this in the local universe. We don't even see this in the distant universe. This would be an incredibly fast, incredibly energetic, and just a violent process for all of these stars to form so very quickly. It's not something we were expecting at all, though there are hints in both earlier times and in later times that perhaps this process isn't as crazy as we would have thought 6 months ago.
Right. And I know like other surveys and stuff are turning up similar related results. Definitely the general opinion is that the universe was coming together a lot more quickly than anybody ever expected. So I guess, what do you think what are the implications to some of the other sort of larger questions that we have in astronomy? Things like, how big were the first stars? How do we get out of the epoch of, how do we get into the epoch of reionization? Do you think that this research has some implications for some of those questions?
Yeah. So I would say, in order to form a system such as this, you must have an extremely rapid pace of turning gas into bright young stars. And so if we have a lot more young stars forming a lot more quickly in the early universe than we previously suspected, these stars are going to do a lot of cosmic work. One of the things that we think they could do is generate a ton of ionizing photons, and that could certainly affect the rate of reionization, not only globally, but also in these big ionized bubbles directly around the forming systems. The rate of ionization of the intergalactic medium nearby would be, I suspect, quite high. If we're forming all of these energetic young stars, it's hard to get around that. So that would be a very interesting implication. And also, if confirmed, these objects have something like 20 times the total mass density of all the other galaxies we had detected at this epoch. So the amount of stars in the early universe just jumps up dramatically. If these are correct.
Right. And I think like that epoch of reionization, this time when the universe went from being fairly cold and dark to being ionized again, this is one of these big mysteries. Like, was it quasars that were able to heat up this gas and dust? But if you have this level of furious star formation going on early on, like, that solves it, right? Like, boom, you've got radiation leaking out of these galaxies into the surrounding gas and ionizing them again.
Yeah, I mean, we haven't done the calculations to say whether or not it solves it, but I would say there are three prevailing theories right now for how the universe was reionized. One is quasars, one is tiny little blue things, so a lot of tiny galaxies, and one is called, one paper put it, reionization by the oligarchs. Yes.
I haven't heard that one.
It's a rich term, if you will. But yeah, I think finding that these oligarchs are not only present, but indeed far more massive than we had expected and far more mature.
Right.
We lend a lot of credence to this theory for reionization by the oligarchs.
Yeah, and there was a paper that I just read where other people are sort of made a similar measurement using a different mechanism. So it seems like we're starting to trend towards star formation, these oligarchs, right, leading to the reionization, which is quite exciting because, again, this is one of the bigger mysteries, but what JWST was designed to solve. So I guess, the job of a scientist is to be skeptical, and you mentioned this right early on. So tell me how you're wrong.
I love that question. There's a couple of ways we're wrong. First off, let's assume they're galaxies. There are a couple of possibilities for how our estimates could be pretty far off. One is that, we're sort of implicitly assuming that these things work like nearby galaxies. So the stars, the gas, the cosmic dust, the black holes, they all behave as they do in our models, which are calibrated on nearby objects. But this is a real frontier. I mean, the early universe is an exotic place where heavy elements like carbon, iron, oxygen are far more scarcer than they are today. So our recipes may not be perfect. Our models for stars with very small amounts of heavy elements in the early universe, they're not so good. And so one way to make these masses much lower is if something called the stellar initial mass function varies even modestly with time. We don't have hard evidence that this happens so far, but it's also hard to rule out. The stellar initial mass function is like, if I have one really massive star, do I have two little stars? Do I have four little stars? Do I have little stars? That's what it is in a nutshell. And so all the mass is in those little things. So if this ratio varies, we only see the bright stars, but we infer the mass in the little stars. If this ratio varies dramatically, well, we have a very different picture of these.
Yeah, I mean, that's even a question that people are still trying to sort out in our stellar neighborhood. I mean, we can only see the bright stars. We have a hard time seeing the red dwarf stars. We don't know how many of those M dwarfs are around us, even within the nearest 100 light years of us. So trying to figure out the distribution of these at, light that's been traveling for 13 billion years is next level. So then what will it take? We mentioned early on, and I sort of excitedly thought about the spectroscopy, and you're saying that you haven't done that yet. So explain to me, like, how you're going to get the spectra of these galaxies.
Yes. So we do have James Webb's time is very valuable. It's the only instrument we have that can get a good spectrum of these types of objects. And so right now, a few programs have been slightly diverted, maybe the telescope tweaked slightly. So we have spectra of a couple of them. One is a black hole. Another two are galaxies. So we have tentative evidence that it's going to be a mixed bag, which is not a surprise. And to be clear, if a couple of these pan out, it's still a dramatic increase in the amount of mass at this epoch. So we only need a few to really change our picture.
Right. If only some of the newborn babies turn out to be adults a couple of days after, it's still quite surprising.
Exactly.
Yep. So this is like, you haven't published it in a paper yet. You're giving me a sneak preview of the research that you've actually confirmed the spectra on a couple of these to be actually galaxies.
One of them is published. Some of them are unpublished.
Okay.
The great majority of them still need spectra, and so we're working on that. At this point, to get a spectra of them, we need to submit a full proposal, have it go through peer review, have all the scheduling be done. So it's going to take, of course, a quarter a year to really delve into this.
And so, like, based on what you've seen and what you're thinking about, I'm trying to think about like how you digest this, because it feels, kind of similar. Okay, so like you think about the crisis in cosmology, right? This Hubble tension. It's causing astronomers to kind of go back and rethink everything that they're doing, thinking about trying to redo the measurements, but they feel pretty confident in the measurements. So now you've got questions about, do supernovae explode with a consistent brightness? Are there other things that are happening? So, and it almost like, I'm trying to describe this, it's almost like at an emotional level, you come back and think about star formation and galaxy formation, all of that. How would you chart a path forward to get to the bottom of this mystery, do you think, for you and other astronomers? How should the astronomical community respond to something so shocking, if true?
Yeah, well, that's an excellent question. And whenever we find something that makes us go, it's really good to start kicking around our assumptions and making sure they still hold. And so these objects, I mean, at face value, they are they're not at all what we expected, and they're sort of on the edge of believability. And so whenever we're at that stage, it's good to start going back to the basics and start kicking them around and seeing if they still hold. And so one of the basics I mentioned is the stellar initial mass function. That's a really tough one to test. But if this particular foundation shifted even in a modest fashion, it would also completely shift our theories for how galaxies form, because everything is based off of this.
Right.
So we need to start really thinking about the fundamentals. Our models for how stars work with very low metal content, our models for how cosmic dust is arrayed in the early universe, our models for star formation in the early universe. And so things like this are great catalysts to start thinking very carefully about our established theories and see what might give or maybe has a little more wiggle room than we thought before. This kind of study is so remarkable that I suspect we're going to find a number of things. I suspect we'll find that galaxies did form a lot faster than we thought, and also that we're making some mistakes, and also that some of these are shockingly bright supermassive black holes. I really bet we're going to find all these things, though.
Right, yeah. Yeah, I mean, I think about, like, say, people trying to search for the missing matter in the universe, not the missing dark matter, but just the regular missing matter. And now I think we know what it is, and it ended up being probably 5 different phenomena, that there's some, missing material in intergalactic gas, there's other stuff. And do you think that, it'll be very similar, that there's not going to be one completely different thing, but there's like a whole bunch of small pieces that when you add them all together, you get this result? Or it's some one big thing?
Yeah,
like,
I mean,
it's dust. Turns out it was dust.
I think that is an excellent analogy, and I don't know what we will find. If I had to put money on it, I would bet we're going to make a number of discoveries, each of which will incrementally sort of put these in their place. But I don't know what we're going to find, and that's part of why this is so exciting. A lot of science moves on slow timescales. It takes months or years to find something new or really blow our socks off. But this came right out of the first images of Webb.
Yeah.
We were expecting to find amazing things. We weren't expecting to find these right out the gates. So we've been focused on confirming they're real. The next step, and it's going to be a big one and probably a long one, is figuring out what caused them and how to change our theories to bring them back into the fold, if you will.
Right. Now, there are a lot of less careful publications than Universe Today, which is our organization, who are running fairly clickbaity titles about how, like, we don't know the age of the universe, that Webb is overturning the Big Bang, all that kind of stuff. How would you push back against, or help inform people who have sort of heard that narrative, as a person who's actually working on this, to sort of set them straight?
Well, that's an excellent question. I really appreciate it. The universe, the age of the universe is something like 13.7 billion years, plus or minus 20 million. It's known to high precision. Lambda CDM, or prevailing theory for the cosmology of the universe, has passed dozens of tests with flying colors. I don't think that finding some objects in the very first month of Webb is going to overturn an it's an old theory, and it's very well established at this point. The tools we're using, they are reasonable heuristics, and we're doing our best. We're a team of international experts, but we're not going to break the universe immediately. With extraordinary claims it requires extraordinary evidence, as everyone knows. And I would say our evidence is strong circumstantial evidence that something weird is going on. But we really need to study this in much greater detail and understand exactly what's happening. If we were to break Lambda CDM at any point in the future, I would be very surprised if we did it by analyzing the masses of stars and galaxies. It's an uncertain science, and there are many ingredients, all of which might change with time in a way that would lead to results that look shocking, but might instead be better viewed as a way to question our underlying models. So I think sort of we've got like a rubber hammer, which is our tool of inquiry for galaxies, and we're hitting against a steel wall, which is Lambda CDM. It's going to take a long time to get anywhere, and we have to be really dedicated to do it.
Right.
It's not impossible, but I would say we need more evidence.
Right. Yeah. And if you did break the steel wall with your rubber hammer, you would love that.
Oh, it would be incredible.
Right.
Yeah, it would obviously be a fantastic discovery. But we really need to make sure that this is the right path, and I suspect we will find that there is something else going on before we'll break Lambda CDM. But it's important to keep an open mind.
Well, right. But I guess my point of that is that, like, a lot of people who sort of roll their eyes in the comments and make posts on Facebook and stuff, they allege some kind of conspiracy among scientists and think that you're trying to repress their personal theory that they've developed for whatever. And I think the astronomy community would absolutely love to overturn longstanding theories. That's how Nobel Prizes are earned. You're all trying to overturn theories and would love to see the results of this. And so, I don't know. I just find that, that allegation kind of ridiculous. And so I think, this just kind of confirms it for me.
Yeah, no, that's exactly right. If we overturned Lambda CDM and we believed it, we would be shouting it from the rooftops. We would be extremely stoked. I would be on the comments section and YouTube typing away my conspiracy theories.
Right. Yeah. How come everyone is, that would be hilarious. Yeah.
Yep.
Awesome. All right. Well, Joel, if people want to keep track of your work, what's the best place to do that?
Yeah. Well, apparently on your YouTube channel.
Yes. Yeah.
I'm an assistant professor at Penn State. We publish our research findings very often, both on the archive, on our website, and increasingly recently with the launch of James Webb in the media.
Wonderful. Well, when you do get confirmation or even better, figure out why this is happening, would you let me know?
Absolutely. I'll reach right out.
Wonderful. Thank you so much.
Thank you.
You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word. There are no ads and it's absolutely free. Subscribe at university.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at university.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to David Giltonen, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbeoff, Josh Schultz, and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us.